Dear ladies and gentlemen, I wish you a very nice evening. Now, I would like to think with you for a moment about the problem of real water scarcity. Imagine you have to gain water in a very dry and arid land. One could drill a well, or wait for water to collect it, or just order a water truck to bring the water from far away. But what if none of these were allowed? What if all the conventional methods were hopeless and impractical? Ladies and gentlemen, the picture you can see here is an utopic design of a new concept of water supply. During my bachelor thesis, I was able to develop a device that gains fresh water in a very unconventional yet interesting fashion. Today, for the first time, I'm excited to share the results with a larger audience. My name is Igor Luketina, and I'm a bachelor student of civil engineering and water management at the University of Natural Resources and Life Sciences in Vienna. So let's see how we can make use of humidity and what an alternative fresh water supply is all about. Since the bachelor thesis was part of an EU-funded project, I had a strict and die-hard framework. This means that an alternative water resource was the main task. So as said before, no rain, no groundwater tapping was allowed. As things in our environment are getting serious, and anything other than an environmentally friendly method would be silly. That's why a big amount of attention was paid to sustainability in terms of materials and design. As if this wasn't challenging enough, the company I was working for, or I am still working for, has an innovative spirit. So we concluded that solid state and innovation in general are the way to go. With the set framework, we condensed the problem down to one possible water source. It's atmospheric water or less scientific humidity. It is the most evenly distributed water body on our planet and represents a yet untapped source of water, the atmospheric water. There were attempts about 100 years ago by Russian scientist Zebold to collect dew in large amounts, but was fairly unpractical due to big dimensions and very low water output. Since the late 2000s, fog catchers are developed in Chile and they are suitable for some regions with frequent fog occurrences. However, the water flower we discuss here is by no means a fog catcher. It rather uses the principle of condensation and dew formation. But how do you make the dew work for you as a water supply? First, we have to understand how dew occurs naturally in order to seek for ways how to enhance it for human needs. What is dew? Dew can be described as a water droplet that forms upon a surface that cools below the dew point. It sticks to the object and can be observed in nature mainly at night and in the early morning hours, because the night sky is the window to the cold universe and the sun cannot heat up the flower. Some cultures attribute it an aspect of eternal youth and youthful beauty. We are a little simpler and more practical and would only like to gain fresh water. So passively this flower here has collected dew water. It happened because the outgoing energy was bigger than the incoming, thus the surface temperature dropped below the dew point. If we have a look in the infrared spectrum, we can determine the various energy fluxes. As said, there are incoming radiation and outgoing radiation. Of course, the ground is still somewhat warm and the air too, so they are usually positive energy fluxes. As water goes into the liquid state, it releases a considerable amount of energy called latent heat of enthalpy. If all these energies result in a low surface temperature, the humidity will form droplets and voila, we have dew. Basically, you end up with an energy balance like this one. As I wanted the incoming to be low and the outcomings to be as high as possible, I adopted the design and material. So by its design, the water flower is windshielding the surface. A special high emissive coating amplifies the outgoing radiation by almost 50%. And insulation effectively stops the energy flux from the ground, but as more water condenses, the heat increases significantly. To keep the temperature low, I decided to actively cool the flower. How, we will see in just a moment. After the assessment of the influential factors of dew, my colleagues and me could discuss the design and proper materials. The water flower is a little bit different than the one from the first slide, but the idea of the alternative water supply remains the same. So the condensation here happens inside the funnel. The droplets then trickle down to the lowest point where the water gets collected and stored in a water tank. The insulation is made of natural hemp plates, and inside there is aluminium sheet metal. The sheet metal is painted with a high emissive white coating. Basically, the device can operate passively or actively by enhanced cooling. Passive means no energy is required to extract the water from the humidity, and active means there's additional thermal elements which are powered by electricity to actively cool down the surface further. So the gray plates are representing the heat exchangers of the enhanced cooling. This is the final prototype. In fact, the water flower serves as a rainwater collector as well, but rainwater collection is not considered in the development, neither in the effectivity measurements. So there are three models with these measurements as relative comparison between no painting and with painting and with active cooling and painting. So before we have a look in the results, I would like to discuss the active cooling by thermoelectric elements with you. We use this technology because it is a solid state and has no emissions except of excessive heat. No noise and no moving parts seem to make the Peltier elements a perfect cooling device, but as it is with technology, there are some drawbacks to it. High cooling power results in high currents, and the efficiency is about a maximum of 50%, and this is only if the waste heat control is done properly. So if you have a look inside of a Peltier element, there are semiconductor couples which, when voltage is applied, they build up a temperature difference between two sides. The water flower operates a 4 by 4 centimeter and a 4 millimeter thick Peltier element like the one on the picture here. After some lab testing, the thermoelectric cooling units, the results went in a thermal simulation of the condensing surface. We have 2 cooling units per surface, resulting in a total of 12 units for one active water flower. The simulation shows one surface with temperatures below 17 degrees and in the center spot about 5 degrees Celsius. The heat sinks are still massive because the generated waste heat has to be drawn away from the Peltier element to secure no drop down in overall efficiency. Now we can dive into some first-hand testing and look at how much water we actually produce. The prototypes were set up to check the efficiency of the high emissive coating and to find out the water output. This setup back in 2019 included 1 active and 2 passive water flowers. It was done in the garden of the associated company in Vienna as a real environmental testing. It results that an active water flower with high emissive coating can provide up to 350 milliliters of water per night. On average, the actively cooled water flower generates 200 milliliters and relatively compared almost 4 times as much as the 2 passive ones together. The passive with coating compared to the one without has almost 50% more water yield than the one without painting. Noteworthy is that the active type can be let turned off and operate as a passive water flower as well, but on average it uses up to 140 it produces 140 milliliters per kilowatt hour. This can be reduced by a significant amount if the control of the Peltier elements gets refined. Since the concept is meant to relieve water pressure in arid areas, Vienna is not a very representative location for such a case study. As part of the European project, I went with a colleague to Tinos to build up the second testing. It is operational in this very moment and logging data since October. Tinos experiences a typical Mediterranean climate and has warm and dry summers and mild winters. The water scarcity comes from a disrupted groundwater body, which can no longer hold fresh water to fulfill the needs of agriculture on the island. Important enough is to note that on the island you come across very strong winds. According to Greek mythology, the god of winds was born there. The winds become so strong in the afternoon, but fortunately die down at night. But sometimes they last for days without a break. This is where the second setup is located. This setup will show us not only a comparison between active and passive, but also the dependency of water output on environmental conditions. The productivity of the passive depends entirely on the environmental conditions, since it is set free to interact only with the surrounding. Weather data is constantly being observed, as well as surface temperature of the two water flowers. Especially wind speed and cloud coverage determine whether the surface temperature drops below the dew point or not. Unfortunately, the water metering device is not logging as planned, so we have only data for surface temperature to represent if dew occurred or not. But let's have a look at the results. As said, the surface temperature determines the water output. Is it well below the dew point, then condensation occurs. Here we have a temperature profile of 4 days from 3 weeks ago. Sub-zero doesn't mean freezing water, it means that the surface temperature is lower than the dew point in this very spot, and therefore dew formation occurs. This is where we harvest fresh water from humidity. We can have a look at the night of October 29th. We had an overall condensation time at least 5.5 hours. It is important to say that the active water flower right now is running at only 40% power, which is provided by solar panels. Due to the current situation, we have to wait for the Greek borders to open. I hope that after the restrictions, I can modify the water flower to operate on 100% of its potential. Dear ladies and gentlemen, as rough times are approaching for our societies, we must confront problems as water scarcity with courage for the unfamiliar. If we use our scientific knowledge and technology in an interdisciplinary way, we could revive arid regions with all the positive side effects. This is how the water flower could look like, giving shadow to the plants during daytime and irrigating during nighttime. In general, optimal designs for such water supply technologies still require attention in the field of material research, especially for dew harvesting. A universal guide value for dew would facilitate further research. Furthermore, an adopted power control for thermoelectric coolers would significantly increase efficiency. With this contribution, I hope to give sensible solutions for water relief in arid areas. I am excited to learn what type of findings will come in the near future. I would like to thank my supervisor Thomas Ertl for his open-minded viewpoints. Special thanks goes to Helmut Schabschneider, my colleague during development and testing. The EU for funding the Hydrusa project in Greece, as well as Pepe, Johannes and Linus from Alchemia Nova. If you have any questions or critics, now is the time to raise them. If you want to contact me, please do so via the email down below. I am more than glad to hear input from you. Have a nice evening and take care.